Today we are going to study quantum noise and quantum operations. So, well, one of the postulates of quantum mechanics was uh, when you have a closed system, you have a unitary evolution. So, rho at a future time is given by a unitary evolution. But in the real world, there are no closed systems. A closed system is at best an approximation. So how do we do quantum mechanics? We need to go beyond. We need to go beyond unitary evolution. And when we treat system as well as the environment together, uh, that is called the study of open quantum systems. Or more generally an open system. So I have the system and I have the environment. So an open system is essentially the dynamics of the system plus environmental interactions. Mathematical framework to describe open quantum systems is the open quantum system formalism. Uh, and this essentially is also responsible for the noise in the system, disturbance due to the environment, and we are going to look at the quantum noise as well. Now, let's look at noise in classical systems. And let me label this topic as classical noise and Markov processes. So consider a classical bit. In an environment. So by classical bit I mean something that takes 0 or 1. It can be a bit on the hard drive plus the environment can be stray, magnetic fields, and I have the bit 0, I have the bit 1. Due to the interaction with the environment, the stray magnetic fields, I have a probability, some probability of the bit flipping. Let me call this P. And with 1 minus P, the bit remains as it is. Similarly, let me say that the probability of flipping 1 to 0 is also P, and 1 remaining 1 is 1 minus P. These P's, the probability of 0 flipping to 1 or 1 flipping to 0 can be different. Let's just take it in the most simplest case to be equal. So how does one determine P, for example? The probability of flipping. So for that, one needs to model the environment. And the environment consists of stray magnetic fields. So essentially, magnetic fields in environment by that I mean the model of the environment, plus the interaction between magnetic field and our bits, and our bits. What is this given by? Interaction between, let's say, our bits were some charges. This is given by Maxwell equations, all the electromagnetic interactions. And using the model of the environment, the distribution of magnetic fields, and the interaction of magnetic fields with charges, one can estimate the probability of flipping. Now, one may ask the question that if classical mechanics is deterministic, whether it's Newton's laws, it's Maxwell's equations, why is the bit flip probabilistic? Probabilistic, or given by some probability P. Well, the short answer is that in general, the environment has many degrees of freedom, maybe possibly infinite degrees of freedom. Many degrees of freedom. And when we model an environment, we take into account average effect of environment based upon statistics. And this gives rise to us assigning probabilities to things like bit flips and so on and so forth, and other errors. Remember, in the first few lectures we talked about subjective ignorance. A coin toss is random because I do not control all the information about the coin toss, the torque I apply on the coin, the air pressure, so on and so forth. So that gives rise to probabilistic processes. So more formally, let P0 and P1 be the initial probabilities for states 0 and 1 respectively, and Q0 and Q1 are the corresponding probabilities after the noise process. So let X be the initial state and Y is the final state. The probability that the final state is a specific Y is summing over X all the conditional probabilities that Y was indeed Y given X was X. This is the conditional probability of finding of the flip of the transition from X to Y multiplied by the initial state was indeed X and summing over all X. So the probability of finding the final state Y is given by the conditional probability of transition from X to Y times the probability that the initial state was indeed X. So these are the transition probabilities. So we have Q0, Q1, the state after the noisy process, is given by the transition matrix times the initial probabilities. And the transition matrix according to was 1 minus P2 retain, P2 flip from 0 to 1. So this is a symmetric matrix in this case. Let's consider a slightly more complicated process. Let's take a classical circuit. It's a very simple circuit. I have a bit X and I have a NOT gate cascaded with another NOT gate. And finally I have, let me call this, I have an intermediate state Y. And then I have Z. This is gate 1. This is gate 2. It is reasonable to assume that the errors of gate 1 are independent of errors of gate 2. And this is known as the Markov process. When errors act independently, or shall I say consecutive noise processes act independently of each other, independent of each other or independently of each other. The environment, of course, the hidden assumption is that the environment causing the noise process on gate 1 is independent environment causing noise on gate 2. A single state noise process can more formally be expressed as the state Q times a evolution matrix applied to the initial state. So this is my single state noise process, and E is called as the evolution matrix. It tracks, or it's responsible for the evolution of the initial state P vector to Q vector once the noise process has been applied. Now, one might ask, how does this translate into the quantum case? Well, in the quantum case, Q and P would be replaced by density matrices, because that's what describes the state of, so these are vectors, two-dimensional vectors, the classical state. Eventually, this is going to be replaced by the quantum state. So, just for the classical state, what are the properties of, what are the properties the transition matrix or the evolution matrix E? Of course, as you can see, the columns of E should sum to 1. And why is that so? Have to sum to 1. What happens when you're applying some E to the state 1, 0? Well, the probabilities need to be conserved. So the columns have to sum to 1. So if this is 1 minus P, this has to be P. Similarly, when you're applying E to the state 0, 1, these two guys have to sum to 1. Secondly, there's a positivity requirement. If the input state is a valid probability distribution, so should be the output. That means it should take a valid probability distribution to a valid probability distribution. So if the input is a valid probability distribution, so should be the output. And that requires all entries of E should be positive. So that was so far about the classical operations. What about quantum operations? We can probably begin it on the next page. So classical states are described by a vector of probabilities. Quantum states, as we have seen, are described by a density matrix. So classical states are described by a vector of probabilities Quantum states are described by a density matrix. So I have classically an evolution matrix times the initial vector. Quantum mechanically, I have a density matrix going through a process. So this is my initial matrix, and this is my final after the quantum operation. So this map is called a quantum operation. For example, well, we already have examples, the unitary evolution. That's a quantum map. Any other example? Well, we just saw quantum measurements. That's a where these guys are the measurement operators. Notice I'm not normalizing the state right now, but the bottom line is that it is describing some process, let's say unitary evolution or quantum measurements, and that is my analog of a quantum operation formally. So it turns out that there are three separate ways of understanding quantum operations. So what can we do? One is we can model the system plus environment dynamics. And this is the most concrete way in some sense where I have to take into account the interactions between system and environment, take account interactions between system and environment, between system and environment. The downside is that this is not great for calculations. There is another way, intimately connected. It's the operator sum representation. This is abstract, but we can great tool for calculations. And the third way is an operational interpretation. By what we mean that we just demand what do we ask from a quantum operation, or physically motivated axiomatic approach. So the advantage over here is that it will include a very wide spectrum of quantum operations. Remember, the bigger picture, we are trying to study open quantum systems. A quantum system is never isolated. How do we study that? And the fact that quantum system is never isolated, there are always some stray magnetic fields, so on and so forth. That's the source of the fundamental quantum noise in any experiment. Uh, how do we study that? We study that through, there are three ways. By the way, all these three are equivalent ways, as we will show. Uh, and Either we study more concretely the system and the environment dynamics, or the operator sum representation, we'll get to that, or an axiomatic approach. So conceptually they offer useful insights, and all three are equivalent. So for example, let's look at so conceptually each of the three offer insights, and one might have an advantage over other in cases, and all three are equivalent to each other. So with that, let's look at the first one, which is the system environment dynamics, or let's try to study the environment and quantum operations. So a natural way of describing a quantum operation in this way is, you start with the system, and of course I have an environment. Let's say they start in a tensor product. That's the state of the joint state. Let me call it rho joint. So what happens? I have a system, tensor product into an environment. It undergoes some unitary evolution. Remember, the evolution on the system itself was not unitary because I had environment, but I go to a larger system and environment, that's a unitary evolution, and then I trace out the environment using our partial trace formalism. And that gives me a quantum map just on the system. So in other words, I have the system, I have the environment, I allow them to evolve, and I just consider the system. This is a very powerful formalism, of course. And what are the assumptions here? The assumption is, well, the environment starts in a product state with a system, a tensor product state with a system. Also, and that's a reasonable assumption actually, because when an experimentalist prepares the initial state of the system, all correlations between usually system and environment are done. Initial state preparation is in such a way that all correlations between the system and the environment are undone. Uh, Second is that, uh, well, one concern you might have is that the environment might have infinite degrees of freedom. Then how is it possible to specify a U? Uh, Very interestingly, it turns out that if the system has dimension, we are going to prove this as well. System has dimension D. Any possible transformation rho gives me can be described by an environment of no more than d square dimensions. So this is a remarkable fact that no matter what the heck is happening in the environment, how large is the environment, as far as the system is concerned, the transformation on the system can be modeled by an environment of at most d square dimensions. And of course, not of course, but one thing more to be noted, we are going to show this also. The environment need not start in a mixed state. A pure state would do. So, as an example, let's say I have a system and I have an initial environment in state 0. This is environment. And the dynamics is just a C naught gate between the system and environment. And after tracing out the environment, I'm just interested in the map or what's the effect on the system. And this was my formalism. I start with the system, tensor product with the environment, and we apply unitary, which in this case is the C naught, and we trace out the environment. It can be shown that the resulting quantum map which I get is given by this guy, where my P0 is a projector just on the system and P1 is also the projector just on the system. So the effect of an environment interaction of a C0 gate between system and environment, tracing out the environment, is equivalent to the action of projectors on the system. So far we've considered quantum maps that take inputs as a state of the system and gives output as a state of the system. But the theory of quantum operations is far more richer. Your input and output spaces need not be the same. So for a quantum map, input and output spaces can be different. For example, row A is the initial state of the system. Let's say it's a qubit. And this interacts with row A, or this system interacts with, let's say, a 3-level atom in some standard state, in a state. Now I can define a quantum operation as I start with a tensor product state of the system and the environment. I apply a unitary and then I trace out the system. So over here, I have a quantum map or a quantum operation which takes an input as the density matrix of the system and pops out the density matrix for the environment. Can map input and output states that are different. In general, we are usually concerned with the effect of environment on the system itself. That's why we keep the input and the output spaces of the map same. But the theory of quantum operations or quantum maps or quantum noise is rich enough that our input and output states spaces need not be the same. Yet the formalism is powerful enough to describe those scenarios as well.